This is Shane Picard with another geometry lesson. Today we're talking about the law of sines and the law of cosines. Until now, the ratios we've studied in trigonometry, sine, cosine, and tangent, have all applied to right triangles only. Now what we'll do is extend rules that we've learned in order to find values in non-right triangles, such as obtuse and acute triangles. The first law we'll look at is called the law of sines, and I've stated it here. It says that A over the sine of A is equal to B over the sine of B is equal to C over the sine of C. Before we can make sense out of that law, we need to talk about a naming convention. It's a standard that most teachers of geometry use. Most texts apply the same naming convention. We need to talk about it right now. If you look at this triangle, it's triangle ABC, and you'll notice the variable little a across from angle A. You'll notice variable B across from angle B, and you'll notice variable C across from angle C. That is pretty standard. What it means is that I'm using variable A to represent the length CB, and that A is always across from A. B is across from B, and C is across from C. It's somewhat important that we understand that, and perhaps more particularly, that we don't confuse the different letters. We don't confuse angle A with length A, or angle B with length B, etc. So that's the naming convention. And when we use that convention and look back up here at the law of sine, we can see that what it really says is that the ratio of the length of a side to the sine of the opposite angle is consistent in any triangle. So you can see that no matter which angle I pick, if I take the sine of it and compare it to the measure of the opposite side, those three ratios are equal in any triangle. It doesn't matter if it's right, obtuse, or acute. They'll always be equal. That's the law of sines. Before we apply the law of sines, I'd like to take a moment just to prove it. To do that, the first thing I will add here is the altitude to point C, and we'll call that H. When I drew in that altitude, notice that I created two right triangles, one here on the left and one here on the right. Now there's actually some ratios that we can use, particularly the sine ratio, because we're dealing with right triangles again. So let's look at the triangle on the left first. The triangle on the left, you can see the following relationship, that the sine of A is equal to opposite, which is H, over hypotenuse, which is B. So the sine of A is equal to H over B. Meanwhile, the sine of B down here is equal to H, the opposite, over A, the hypotenuse in that triangle. I need to change these around a little bit. I'll multiply this top one by B, and I'll multiply the bottom one on both sides by A. And so the B's here cancel and the A's here cancel. And in the top one, I end up with H equals B sine A, and the bottom one I end up with H equals A sine B. You can see that these two expressions have an H on one side, and so therefore using the substitution property, or the transitive property, we can say that A sine B equals B sine A. Now we can rearrange this to read as follows. If we divide both sides by the sine of B and divide both sides by the sine of A, you can see that on the left sine B cancels, on the right sine A cancels, and we end up with A divided by sine A equals B divided by the sine of B. And we've just proven at least one piece of the law of sines. It'd be a good question to ask, well, wait a minute, what about this other piece? We could do exactly the same process, drawing in the altitude here and repeating the process for the other sides. Or in the altitude here and repeat the process over there. If we did that, we would find that all three of these ratios are equal. Let's go ahead and apply the law of sines now. We have triangle ABC here. You'll notice that the length of AC is 7. That length, of course, would be equal to B, based on this naming convention. And I have angle C and I have angle B. So how do we set it up? I'm going to place 7 over sine 77, that is b over the sine of angle b, and say that that is equal to c is what we're looking for, divided by the sine of 82. So I'm comparing these across in ratios. Now all we need to do is multiply both sides by the sine of 82. And we end up with c is equal to the sine of 82 times 7 divided by the sine of 77. Now we need a calculator. Going to the calculator, we need to multiply sine 82 times the ratio 7 over sine 77. Probably the easiest way to do that would be to put the 77 in and then find the sine of that, which is 0.974. I'll store that in memory. And now we'll go ahead and take the sine of 82, multiply that by 7, and then divide that by the sine of 77. And we end up with 7.114. So C is approximately 7.114. And that's the value that we have over here. So that's how we use the law of sines. Notice that if I wanted to find CB in this problem, which we would denote with the variable A, we can use the triangle angle sum theorem to find the measure of angle A. And then again, I can draw a comparison here and here using the law of sines, and I can find that value very easily. Let's look at the law of cosines. The law of cosines is stated c squared is equal to a squared plus b squared minus 2ab cosine c, where again we use the exact same naming convention. C is the length of the side opposite angle C, and by the way, that is important that we realize that's a lowercase c there. A is the length of the side across from angle A, B is across from angle B, and then of course A and B are those same values, A and B. And then cosine C, notice the capital C, that is this angle C. Let's take a look and see how the law is applied. This particular problem, we have known length B, this is B over here because it's opposite angle B, and we have a known length A, and let's try to find this length AB, which we'll call lowercase c. Let's try to find that c. How do we set it up? Well, we just plug these numbers that we have available to us into the law of cosines. C squared is equal to a squared, so a in this case is 4, so that's 4 squared, plus b squared minus 2 times a times b times cosine of 75. We've got all the variables in there. To solve for c, you'll note that we need to take the square root of both sides. And so now it's quite a long expression. Let's go to the calculator and see if we can come up with a number. I'll start with finding the cosine of 75, since that number is maybe the more complicated of those values in the radicand. So 75, find the cosine of that value, 0.2588. And I'll multiply that by 7 and multiply by 4 and multiply that number by 2. We have 14.49. I'll place that number in memory. Now we have 4 squared, which is 16, plus 7 squared, which is 49. And then we need to minus that number from the memory that I just put in. So we end up with 50.5. The last thing we need to do is take the square root of that expression. And so we'll do that now. We end up with 7.1. And that is how we use the law of cosines. These two laws are a little bit difficult to memorize, but if I can just give you a tip with respect to the law of cosines, you'll notice that this piece right here is actually the Pythagorean theorem. C squared equals A squared plus B squared. And that's no coincidence. In fact, if you took the cosine of C when C equals 90 degrees, you'd find that it was equal to 0, and so this piece would cancel out. All of that to say that the only thing we really need to memorize here, in addition to the Pythagorean theorem, is this additional section, minus 2ab cosine C. Those are the laws of sines and cosines. They're useful for finding values in non-right triangles, so it's a bit of an extension from right triangle trigonometry. Make sure you work through some review problems on your own, and as always, if you have any questions, please send me an email.